In this video, we're going to talk about how to calculate the pH of a buffer system. And so the first thing we need to talk about is which chemical reaction you want to use the equilibrium constant from. So if you have a weak acid and a weak base conjugate pair, well, if you have the weak acid in a table of Kas, you want to use that. So for example, acetic acid, where this is the acidic proton, donates that proton to water in an equilibrium to give H3O plus and acetate. Now this equilibrium is highly shifted over to the reactant side because K is actually very small. That number is known, and that's about 1.8 times 10 to the minus 5. So a very reactant-favored reaction. But in a buffer, something different has been done. In a buffer, you take acetic acid and you actually throw in a whole bunch of the conjugate weak base, the acetate. So you take a salt of sodium acetate and dissolve it at the same time. And now we have substantial amounts of both reactants and products. And so what's going to happen is that this number is a constant, and these two are going to be significant and nearly equal to each other in most buffers, leaving that relatively unchanged in the buffer system. So if we change these numbers just a little bit by adding acid or base, so if we add some acid, we get a bit more acetic acid. If we add some base, we get a bit more carbonate at the expense of this. But these numbers won't shift that much, and H3O plus will be relatively unaffected. So what we need to do is actually solve this equation for H3O plus and make that our working equation. And so if I have Ka and then I multiply by the acidic form divided by the basic form, then that will simply give me the amount of hydronium in the solution, which then I do minus log to get pH. All right, so let's take a look at a sample problem. Let's calculate the pH of a buffer where the acetic acid has been made to be 100 molar, and the acetate is 0.5 molar. Now this buffer can actually take a lot more acid since it has a lot more of the weak base, but this can also take care of any strong base that you add up to, of course, until the point where this is all gone. All right, so the way you make a buffer is real easy. You take a certain molarity of acid and dissolve so many moles per liter of the salt in there, where the salt ion is the conjugate base, and it's almost like magic. All right, so 1.8 times 10 to the minus 5 is the Ka. These are just numbers you look up in tables. Acetic acid is 0.100. This is 0.500. So it's actually a really quite easy calculation to do. And we get 3.6 times 10 minus 6. Molar hydronium, or H plus. And so we just do log of that. And get 5.44. All right. So a very common buffer is one where you would actually have the same concentration of both of the conjugate pair, the weak acid and the weak base. You can see that in that case, this would be a 1, and so that the hydronium concentration is equal to the numerical value of Ka. For acetic acid, if you were to actually work this out, and you should, you'll get a number 4.75.